Hello friends, let us now learn some important points about film screen radiography. In the previous chapter, we showed how the X-ray transmission image is produced by differential attenuation of X-rays by the organs and tissues within the body. It was seen how subject contrast is influenced by atomic number and density of the overlying tissues and by kilovoltage and spectrum of the X-ray beam. Spatial resolution was shown to be a function of focal spot size. It is demonstrated how contrast is reduced by scatter and unsharpness is influenced by the focal spot size and the distance between the object and the imaging plane. Now this chapter is concerned with image capture on the film, that is film screen or analog radiography. Film screen radiography, image formation. Film. The radiographic image is recorded on a sheet of film, on a sheet of X-ray called as film. The radiographic image is recorded on a sheet of film called as X-ray film. Okay, this X-ray film is made up of, it consists of a polyester base which is around 0.2 mm thick, and it is coated on both the sides with a thin photographic emulsion. And this photographic emulsion is around 5 to 10 micrometers in thick. This emulsion mainly consists of this emulsion in a suspension in gelatin of silver halide crystals, which are generally silver iodobromide crystals with almost 90% of bromide and 10% of iodide. Each of these silver halide crystals are around 1 micrometer in size and contains a million or more of silver atoms. Both films and screens have a very thin, transparent anti-static coat, supercoat, to prevent against abrasion. So there is polyester base, okay, on both the sides of so if I draw, this is the polyester base. On both the sides of the polyester base there is an emulsion. So this is the emulsion which is present on both the sides of polyester base. Then on both the sides of this polyester base and emulsion, there is a protective super coating is present. There is a protective super coating present on both the sides of the polyester base. This anti-static supercoat protects against abrasion and designed not to curdle. The photographic emulsion is sensitive to ultraviolet light and visible light, and it is more sensitive for ultraviolet light and visible light, and it is less sensitive to X-rays. It is affected by mechanical pressure and creasing, by static electricity, and by chemical liquids and vapors, all of which have implications for storage and handling. Then we should learn some important points about exposure to light. The silver iodobromide crystals are present on both the sides of the film, and these silver iodobromide crystals are important. There are two features of silver iodobromide crystals which account for photographic processes. One small proportion of iodine, which is relative to bromide ions. This small proportion of iodine, that is iodine is present only 10%, whereas bromide is present 90%. So this small proportion of iodine when compared to bromide distort the lattice. This small proportion of iodine when compared to bromide will distort the lattice, and the silver halide crystals are manufactured to possess the sensitivity spec. So these silver hydrobromide crystals are structured to possess sensitivity specks on the surface. So on these crystals, you will see that there is a photosensitivity speck. So this crystal, that is silver iodobromide crystal, it absorbs the light photon. An electron gets migrated to this sensitivity speck where its potential energy will be lowest, and when hundreds and so photons are absorbed by the crystal, enough electrons are accumulated in this sensitivity speck to attract mobile silver ions from within the crystal. So these electrons will attract this mobile silver ions when the silver ions are now attached to the sensitivity spec. So these electrons which are accumulated, they attract mobile silver ions from within the crystal to join them, and they are neutralized. They form a submicroscopic speck of silver metal on the surface of the crystal. This distribution of specks of silver within the emulsion forms a latent image. This distribution of silver in the microscopic specks in the crystal results in latent image formation, which is waiting for the development. The next step is processing. Now we have formation of latent image, but this latent image are not visible to the eye. So these invisible pattern of latent image is made visible by processing. The film is processed in three stages. Number one, the film is developed by immersion in an alkaline solution of reducing agent, which is able to enter the crystal at the latent image. This proceeds to reduce the positive silver ions to silver atoms. So this process will reduce the positive silver ions which are present in the sensitivity spec to the silver atoms. So the latent image grows into a grain of metallic silver. The unexposed crystals, so crystals which are exposed to light or X-ray photon, they will produce this silver atoms or metallic silver, and those which are unexposed unexposed crystals, the crystals which are not exposed to X-rays. So this crystal is not exposed to X-ray. So the unexposed crystals which carry no latent image are not affected by the developer. A layer of bromine ions forming the surface of the crystal repel the electron donors or the developer molecule and allow their entry only at the latent images where ion barrier is breached. However, given sufficient time, the developer would penetrate the unexposed crystals. If a sufficient amount of time is given, this developer will also penetrate the unexposed crystals, and this amount of background fog is produced by the development of unexposed crystals is a function not only for development of time but also of developer's strength and temperature. So it is important. The one important thing is the time. So we should place the film into the developer solution for a prescribed amount of time. If that time is exceeded, the developer might also reach the unexposed films or unexposed crystals, resulting in fog formation. The next step, the second step after development, we have to um, fix the image. So the image is fixed by an acid solution of thiosulfate. This acid solution of thiosulfate will dissolve the unaffected silver ions. This acid solution of thiosulfate will dissolve the unaffected silver ions so that the image is stable and is unaffected further by light. So the film is now fixed by acid solution of thiosulfate. which dissolves the unaffected silver ions, so that the image is stable and it is unaffected by further amount of light. For after each stages of 1 and 2, after developing and fixing the film, we have to wash the film. The next stage is washing with water, and finally it is dried by hot air. The result of inadequate washing would be for any retained hypo to turn the film black or brown. So we have to remove the whole hypo or thiosulfate solution which is provided to the film during fixing. So if it is not washed properly and if it is not drained, then the film may turn into mainly brown or yellow with time, causing the stored films to have similar vinegary smell. The automatic processors use a roller feed system to transport the film through different solutions. The processor performance is maintained through a comprehensive quality assurance program. The last topic is that optical density. The film now carries a pattern of silver grains which corresponds to the pattern of X-rays leaving the patient. The image is viewed by a transmitted light on an illuminator or a light box. It is a negative image. So the image that you see on a light box is a negative image where the X-rays have been most intense and the film is darkest. The grain of silver, a grain of silver absorbs the light as it passes through the process of emulsion. So the optical density or blackening of the film. So the optical density or blackening of the film, this depends upon the number of silver grains which are present per unit area. So this optical density is defined as the log base 10 of incident light by the transmitted light. Log base 10 of incident light divided by the transmitted light. This log value is used because the eye responds logarithmically to brightness of the light. Optical density is measured by an instrument called as densitometer, which incorporates a small light source generally in the diameter of 1 to 2 millimeters in diameter and a light detector. From definition, this densitometer can be deduced that if 1% this densitometer can be deduced that if 1% of light is transmitted, then the density of the film will be around 2. If 10% of light is transmitted, then the density will be around 1. The density of a complete transparent film in which no light is transmitted is 0. So densities are additive. If the front and rear end of the emulsion, so if this is the X-ray, front and rear emulsions have a density of 1 and 1. The emulsion which is present in front of the X-ray film and the emulsion which is present behind the X-ray film each have the density of 1, then the total film density will be 2. The density of the area of interest on a properly exposed film averages to around 1. Although in a lung field on a chest film it is around 2. For chest films it is around 2. The density is more than 3 is too dark to be viewed on a standard light box. If the density is more than 3, they are too dark to be viewed on a standard light box and they require bright lamp if details are not seen. So these are the important points about the film screen radiography image formation. In the next class, we will learn about intensifying screens. Thank you.